So you've got to realize that whatever is going to happen after that moment will be publicly posted after a few hours after this seminar, which we find a lot of value in because we can reach out to people who were not able to attend the seminar in person or via Zoom, if you will. These days it's considered as in person today. Anyway, I'm very excited to introduce our today's speaker, Jesse D. Jenkins. And before I will even start the introduction, Jesse, thank you so much for having the time to present, because I know that it's my first kind of experience that this kind of events put a lot of pressure on faculty, because we have to adapt not only personally but also professionally to this environment, and sometimes it takes a lot of extra efforts. So thank you so much for having the time to present. Jesse Jenkins is an assistant professor at Princeton with a joint appointment between the Department of Mechanical and Aerospace Engineering and the Andlinger Center for Energy and Environment. He is also an affiliated faculty with the Center for Policy Research and Energy and Environment at the Woodrow Wilson School of Public and International Affairs. Most recently, Jesse came across my work as the person who probably in our community has the greatest number of Twitter subscribers. He has over 27,000, which is impressive. But also he is well known for his work as an energy system engineer on analyzing and developing feasible strategies to adopt zero carbon resources and to transition the power sector toward what is known as a zero carbon environment. And I hope that he is going to talk about the things more in his presentation. Unfortunately, we cannot clap on Zoom, but let's substitute it with raising our hands. And at this moment, I am turning it over to Jesse. The mic is all yours.
Thank you very much, Yuri. And it's a pleasure to chat with you. I wish I could join you all in person at NYU. But this is the best substitute we have now, and I'm getting quite comfortable yelling into my laptop into the void these days. That seems to be most of what I do with my day. So thanks for inviting me, and it's a pleasure to speak with you. And going to share a bit today about the research at Princeton on how to transition the U.S. energy system to a net zero greenhouse gas emissions world. Which we're in the midst of finalizing now. And so I'll give you a bit of a sneak peek at our Net Zero America study, as well as talk about some of the insights from my prior work on decarbonizing electric power systems and the role of firm low carbon generation sources in particular in helping us get all the way to net zero emissions cost effectively over the next few decades. So I titled this talk Getting to Zero. I've been giving some version of a talk with that title for a couple of years now. And I wanted to start by just framing why are we focused here on achieving net zero greenhouse gas emissions, by which I mean any human-caused emissions of greenhouse gases are offset by a corresponding amount of human-caused enhancements of natural carbon sinks or carbon capture from biomass or the air. And then permanent sequestration of those emissions. So negative emissions that, from human-caused activities exactly equal or exceed the positive emissions from human-caused activities. So why are we talking about this goal? Interestingly, as I said, I've been giving versions of this talk for several years now, really over almost 2.5. And when I started out, it was largely an academic question, right? How do we use energy system models to look ahead to the possible future and think about ambitious climate goals and model what they might look like and kind of get a sense of what might be some feasible solutions and what we might want to tell engineers and utility planners and policymakers about the direction we might want to head. Well, really just the last year in particular, this has gone from very much an academic question to a very practical real world question. As of now, 6 states in the country have committed to, through legislation, statute, or executive order, to transition their entire state economies to net zero greenhouse gas emissions by some future date, generally around 2050 or mid-century. So that includes the states of Hawaii, Nevada, and New York, as well as executive orders in California, Montana, and and Massachusetts. So these are now very much practical questions for policymakers and investors in energy assets within each of these jurisdictions, which collectively represent a size of, would be equivalent to a good sized country. I think, California alone is often said to be something on the order of the 5th to 7th largest economy in the world. So throw in New York, Massachusetts, Montana, Hawaii, Nevada on top of that, and there's a substantial state level commitment in the United States to reaching this goal. And they're joined by several other countries, including the UK, France, and others who have made similar statutory commitments in the last year. At the same time, in the federal government, legislation has been introduced in both the House and the Senate just in the last few months that would, if enacted, would also transition the entire US economy to this net zero goal. And if you were following the Democratic presidential primary debates, which have now wound to a close, every single one of the Democratic primary candidates have committed in one way or another to net zero greenhouse gas emissions by some date between, say, 2045 and 2050. At the same time, we've had a number of individual companies make varying degrees of commitments to net zero greenhouse gases or carbon neutrality or similarly phrased goals, almost all of which have occurred just within the last 12 months as well. That includes a number of utilities, large investor-owned utility companies that serve a substantial portion of the US population, several major airlines, including Delta, Qantas, and JetBlue, and even oil and gas companies like Repsol from Spain, BP, and Shell, just as of today, have made commitments to reduce the greenhouse gas emissions from both their operations and the products that they sell to net zero by 2050 as well. And they're joined by several, mostly European-based minerals and materials companies that produce cement or steel or iron. So these are pretty substantial trends and changes in just the last year that have made sort of research that I do and others like me have gone from very kind of interesting hypothetical engineering problems and academic questions to very real, practical, decision relevant studies, which is the kind of work that I love to do. So I'm excited to see these trends and excited to see the research we're doing take on a more practical and immediate relevance to guide decision makers, policymakers, and planners in a variety of public and private sector goals. I'd like to credit the IPCC's recent special report on global warming of 1.5 degrees Celsius, which came out in October 2018, for really driving a lot of these recent commitments, and the fact that much of the work is now focused on increasing ambition towards net zero rather than, say, more intermediate goals of 60 or 80% reductions in emissions that maybe were more common just a few years ago. This report, which probably many of you heard news reports on or even have read in depth yourself, came out in October 2018, and I think really broke through the news cycle to the public in a way that many other previous scientific studies on climate change have not. And it really laid out in stark terms the trends that we're on, the fact that we're at nearly 1 degree of Celsius of average warming already, and the kinds of impacts that we're seeing from that around the world, from wildfires in California or Australia to more frequent coastal flooding, to increasing intensity of rainstorms and flooding that goes along with that, as well as pointing out that in order to stabilize greenhouse gas emissions, regardless of whether we're aiming for 1.5 degrees Celsius of warming or 2 degrees, we have to get the whole world to a net zero emissions kind of framework in order to stop the increase in atmospheric concentrations of greenhouse gases, and then potentially drive to net negative emissions to reduce atmospheric greenhouse gas emissions and help bring us back from overshooting in the near term the kinds of temperature targets or forcing goals that we might want to achieve. So the IPCC report looked primarily at the goal of reaching stabilizing emissions in a way that led to a decent probability of no more than 1.5 degrees Celsius of warming. And that requires, under different modeled scenarios, basically a central range of somewhere between 2045 and 2060, reaching net zero greenhouse gas emissions for human activities across, this is for carbon dioxide emissions, reaching zero carbon dioxide emissions sometime between 2045 and 2060. And if we target the slightly more relaxed 2 degrees Celsius target, we have to still get to net zero or to zero carbon dioxide emissions sometimes between 2060 and 2080. And then those emissions from carbon dioxide have to go negative, meaning we're absorbing more carbon dioxide via carbon capture from either direct air capture or biomass, which absorb the carbon from the atmosphere initially, and then sequestering permanently that carbon in either geologic sequestration or using it in durable goods. I don't show here the other greenhouse gases. Part of the reason we have to get carbon emissions in particular to 0 and then negative is that it's impractical for us to entirely eliminate greenhouse gases like methane and nitrous oxide that are related to agricultural activities. So most of these pathways require cutting those dramatically on the order of 50%, but some additional direct emissions of other non-CO2 greenhouse gases are likely, and therefore we have to offset those with negative CO2 emissions in order to achieve our overall objectives of a stable climate. The IPCC report also, did a good job of highlighting that while 1.5 or 2 degrees make nice round sounding numbers that are useful for galvanizing political agreements and negotiations, the reality is that every 1/10 of a degree matters, and holding warming to 1.6 or 1.7 or 2.1, et cetera, is better than anything higher than that. And so the challenge is really at a high level, the guidance from science is clear that we need to, if we want to avoid dangerous impacts of climate change, which are already starting to occur around the world, we have to cut greenhouse gas emissions to 0 and then negative as rapidly as possible. And it's that as rapidly as possible part, which is where the rubber meets the road and where engineering systems and policy and politics come together to determine how quickly we can actually reduce greenhouse gas emissions. This is not a scientific statement. This is my normative statement, but I think it has solid grounds that if we are going to try to transition the whole world to net 0 greenhouse gas emissions, and we need to get carbon dioxide emissions to 0 by roughly mid-century, that the United States should lead and not follow or even fall in the middle of the pack in terms of the average trend. So if the global transition needs to occur for 2 degrees Celsius sometime between 2060 and 2080, and sooner for lower targets, the United States should be moving faster than that, both because we have the technological means and the wealth to do more than our fair share of the role. So we can do more, we have the means to do so. And also we arguably have a moral obligation to cut emissions faster than much of the world, given that the United States is responsible for the largest share of historical or cumulative greenhouse gas emissions. And it's cumulative carbon emissions in the atmosphere, not annual emissions, that are the determinant of climate change and global warming. So we have the means to do so and arguably a moral responsibility to lead. And that's where much of my research focuses on how the United States and other developed power systems like Europe or energy systems can transition to net 0 greenhouse gas emissions on a rapid and cost-effective basis. So let's look at the challenge of decarbonizing the United States for the remainder of this talk. I'm going to give you a sneak peek of the Net Zero America study, which is a major effort that has been underway at Princeton even before I arrived in September. And I've joined as one of the co-PIs for this project, along with Eric Larson, who heads the Energy Systems Analysis Group at the Andlinger Center for Energy and Environment, and Chris Gregg, who's a senior visiting fellow at the Andlinger Center as well. We have a large team that's been working on this project, including other faculty at Princeton like Steve Pacala and Rob Sokolow, who you probably have heard of and read some of their work, as well as a great team of postdocs, including Aaron Mayfield, Andrew Pascal, Xuan Zhang, and then a bunch of consultants and experts from other universities that we've pulled in to supplement the expertise we have across various aspects of the study. The study is supported by funding from the Climate Mitigation Initiative and the Andlinger Center, both of which are supported originally by BP and ExxonMobil gifts, by Dow and by the endowment from Princeton University. And we've assembled a wide range of consultants or consultative committee of advisors to review the report and provide us feedback, including those from industry like BP and Exxon, and public interest and environmental advocacy groups, a range of those. So the goal of this study is to provide a blueprint or multiple blueprints in the different scenarios that we analyze to reach net 0 greenhouse gas emissions in the United States by 2050. Our objectives are to provide transparent assessments that are temporally and spatially resolved of the scale, cost, and pacing of required physical, institutional, and human resources that we need to muster in order to reach these net 0 goals by 2050 across the continental United States. The approach that we've taken is to use a large-scale, multi-sector energy system optimization model that we've been working with Evolved Energy Research to deploy for this study, which applies a 14-region model of the continental United States and models 5-year incremental time steps for expansion decisions with operational detail in order to meet a sector-by-sector energy service demand profile projected for each year, each 5-year increment out to 2050. As an optimization model, the goal is to minimize the 30-year societal net present value of total energy system costs, including investment and operation across each of the 5-year increments. It's a perfect foresight model, and it includes seamless integration between the sectors, both of which are somewhat optimistic abstractions of real outcomes. But it allows us to look at linkages and interesting emergent effects as we explore linkage between different sectors, including electricity, industry, buildings, and transportation. Then the real hard analytical work that we've been taking on over the last few months, we finished the modeling work a few months ago, has been to take this relatively coarse resolution model with 14 regions and to downscale and analyze those results at a state or sub-state spatial scale in order to get a much better idea of the key plant and infrastructure investments that have to occur across different technologies and sectors at local levels and how that evolves between now and 2050. I'm not going to have much of the downscaling results to share with you, as that work is just being finalized now and we're reviewing it internally, but I can share some of the insights from the overall modeling results, and I'll drill in on the electricity sector since that's where my expertise and main focus lies. So before we dive into the electricity sector results, some higher level framing, I just want to note that the reason it's critical to do this kind of study now and to look out to 2050, even with the uncertainty that we face and the fact that we don't really know what technologies will cost and what the political environment will look like, et cetera, is that we're dealing with a sector that involves long-lived capital-intensive investments in various assets. And we may not have many times in which those assets turn over or are replaced between now and 2050. So if you think about a complex fluorescent light bulb that lasts for a few years, we will replace those many times between now and 2050. Appliances that might last for a decade will only have a couple of shots at their replacement, similarly for HVAC systems, air conditioning and furnaces. And vehicles last typically for around 15 years after initial purchase. So we really only have one full turnover of the vehicle stock that will occur after 2035. And that means that we really need to be ramping up the kinds of low emissions vehicle sales in the near term in order to ensure that by 2050, we're in a net zero environment. And finally, things like power plants, pipelines, and transmission lines have multi-decadal asset lives. And so from a planning perspective, 2050 is the day after tomorrow for many of the decisions that are being made today. And power plants built over the next 10 years will be in operation through 2050. And if we're not careful on each of these fronts, if we don't plan ahead, implement the right policy environment to induce the smart investments at the time that this capital stock turns over, we risk locking in investments in suboptimal fossil intensive infrastructure that will prevent or slow or significantly increase the cost of transitioning to net zero emissions in the long term. So our goal here is to provide a blueprint for the types of actions that are important to take over the next decade, and some possible pathways that might go beyond 2030 to 2050 so that we can avoid dead ends and we can think proactively about what we need to do now to prepare ourselves for the significant infrastructure investments and transitions needed to reach net zero emissions by 2050. All right, so let's size up the overall challenge. We ran a reference case that uses end-use energy demands from the annual energy outlook from the US Energy Information Administration. So we're not assuming in this study substantial changes in behavior that would drive differences in demand for energy services. So we're not assuming that Americans live in smaller homes or more of us, a greater share than business as usual, or in urban environments with less energy intensive buildings, or that we significantly shift from personal vehicles to mass transit or bicycling or any of that kind of thing. All of those measures are important and would help make this task easier. But to set ourselves up with a conservative challenge and try to meet it, we held all energy demands, end-use energy service demands constant. And what that gives us then is a scenario which, under business as usual, about 23 quadrillion BTUs or quads of energy, about a third of total energy consumption by 2050, final energy consumption, comes from non-hydrocarbon final energy demands for electricity, hydrogen, steam, or biomass that we can very easily substitute zero carbon electricity or electrically derived fuels. And about 2/3 of the challenge under business as usual remains fueled by hydrocarbons, pipeline gas, and liquid fuels. And these are difficult to substitute for. We have much more limited range of drop-in zero carbon fuels available today. And so in order to tackle that remaining 2/3, we have to figure out ways to enhance energy productivity through efficiency or conservation or mode shifting, electrify some or all of those end uses, or some substantial portion of those end uses, develop and use drop-in zero carbon fuels that can substitute for pipeline gas and liquid fuels, or continue to use fossil fuels and offset the emissions of that and that continued direct emissions with a ramp up of negative emissions from direct air capture or biomass with CCS. So when you think about the scale of the challenge, it basically leaves us with 6 options or 6 key pillars of decarbonization. And in our study results, all 6 of these pillars are deployed at scale. The first pillar is energy productivity or efficiency gains in end-use consumption. The second is end-use electrification, where we substitute electric motors or heat pumps or electric boilers for traditional fossil fuel consuming devices, allowing us to use the third pillar, clean electricity, to decarbonize these end-use activities. The fourth pillar then is zero carbon fuels, where we can drop in zero carbon substitutes for a portion of the remaining liquid and gaseous fuel demands. The fifth is carbon capture, utilization, and sequestration, which plays a key role in reducing emissions from industrial activities like cement, large point sources, as well as capturing emissions from natural gas use in power plants and other point sources, and biomass or direct air capture with CCS in order to reduce, to provide negative emissions that can offset remaining fossil fuel use for hard to decarbonize fuels. And then the final key piece, which I won't focus on in this presentation, but is a key lever as well, is to enhance the land carbon sinks in this country. So agricultural and forestry lands that can capture and sequester and store CO2 emissions, and to reduce non-CO2 greenhouse gas emissions like methane, HFCs, black carbon, and nitrous oxide emissions as much as possible. And in this study, we assume that the combination of that 6th pillar of enhanced land sinks and reduced non-CO2 greenhouse gas emissions nearly cancels out, such that we're left with about 170 million metric tons of emissions from non-CO2 greenhouse gas, non-CO2 activities outside of the energy and industrial sectors. And that means that the target for the overall energy and industrial sectors that have to be tackled by pillars 1 through 5 is to achieve roughly negative 0.17 gigatons of emissions by 2050. So we're actually targeting a negative CO2 outcome, just like the IPCC 1.5 degree report trajectories that I showed you earlier for the globe. So electricity and clean electricity is really the linchpin of this overall decarbonization strategy. And that's why I focus much of my own research on exploring cost-effective ways and reliable ways to decarbonize electricity. The first 2 pillars, as I mentioned, are energy productivity and electrification. And you can see how they act together to dramatically reduce the need for hydrocarbon fuels, which is a key component of the overall challenge. So we developed multiple scenarios here. The first I'll point out is a high electrification case in which we electrify most of end-use activities that can be easily electrified, including nearly all light, medium, and heavy-duty vehicles by 2050 are either electric or fuel cell vehicles with hydrogen derived from electricity. And large amounts of electric boilers, industrial activities, and a substantial penetration of end use of heat pumps, electric heat pumps for heating and cooling. And then we did a less high electrification scenario. I hesitate to call it a low electrification case because it's still quite a substantial ramp up from today's levels, but that has less electrification. So those are the 2 panels shown there. The E+ scenario is our high electrification case, and the E- is our less high electrification case. And what you can see is that, first of all, total final energy consumption is down 20 to 30% in this case. And that is a combination of end-use energy efficiency, which reduces energy demand by about 9 quads across each of these cases, or roughly 15%. And then 12 quads of 6 to 12 quads of additional reduction in final energy demand due to the increased conversion efficiency of electric heat pumps and electric motors relative to boilers and internal combustion engines. So since electric motors and heat pumps are much more efficient at converting available energy to final energy services, that also results in a decline in final energy demand. And together that means a reduction of about 20 to 30% in total final energy demand by 2050, even as GDP grows substantially. And in a reference scenario, total final energy demand would be increasing by about 10%. At the same time, we drive total hydrocarbon demand down substantially further by expanding the role of electricity in final energy demand by electrifying or switching to electric fuels in various end-use activities, including road transportation, heating, and some industry, especially iron and steel, and electric boilers as a dual fuel alternative to natural gas boilers in various low and medium temperature process heat. So what that results in then is a roughly 40 to 67% reduction in hydrocarbon demand, which then pushes the remaining pipeline gas and liquid fuel gas demands down into the range that we can cost effectively tackle with drop-in fuels or with continual fossil fuel use and net zero, netting out the direct emissions with carbon capture on biomass or direct air capture. And without that substantial decline in hydrocarbon demand, it's simply not cost effective to decarbonize fully the liquid and gas fuel needs. So this electrification pillar, the expansion of the role of electricity in meeting final energy demands, is a critical linchpin in our efforts to cost effectively reach net zero across the whole economy. This is a closer look at the kind of pace of electrification that we're talking about in the E+ and E- scenarios. So this looks at new vehicle sales. The stock of vehicles, of course, lags behind new vehicle sales. And that means that we need pretty rapid electrification in order to get on the high electrification path, which gets us to basically 100% electric vehicles by 2050. And so by 2028 for light duty cars, 2023 for light duty trucks and medium and heavy trucks, we have to be at 50% of all new vehicle sales are either battery electric vehicles or fuel cell vehicles that run on hydrogen from electrolytic sources. And then in the low electrification case, or the less high electrification case, we basically delay all of that by a decade, so that we reach the 50% point by the late 2030s and early 2040s in that scenario. It also means that in the high electrification case, we reach 100% of new vehicle sales are electric or fuel cell by 2045, versus only 80 to 90% of sales by 2050. And that means that on road in the E- case, we, I think, max out at about 60% electrification in the E- case versus something like 98% electrification in the E+ case. The interesting finding from the study is that you would anticipate that the less high electrification case would have less total electricity demand, that if we fall short in electrification, we have to make up for it through some other means, like increasing biomass or increasing offsetting. When we run our optimization model, though, what we find is that the substitute for electrification is actually more electricity. And that's because in these scenarios, we're basically using all the available biomass we can already. And the only then substitute on the margin for the increased fossil energy demand for gas and liquid fuels that come when we fail to electrify at a higher pace is to produce substitutes for those fuels using electricity as the low-cost carrier. So what we do is we see a breakdown of final energy demand, which is the gray areas, which you can see indeed does fall between the E+ case and the E- case, but is more than made up for by an increase in various intermediate energy demands or flexible loads, which include electrolysis, so using renewable electricity primarily to produce hydrogen with zero emissions. Electric boilers in industrial activities where we install an electric resistive boiler alongside gas boilers so that industrial users can switch back and forth between clean, low-cost electricity when wind and solar are abundant and switch back to natural gas when not. Or even running direct air capture in this scenario, which allows us to increase the negative emissions and use additional fossil fuels for end-use liquid and gaseous fuel needs. All of which are extremely electricity intensive. So you can see we don't really use any direct air capture in the E+ case, but when we go to the E- case, we have to use a lot more direct air capture in order to allow the continued use of fossil fuels and offset their emissions. And we need to produce more synthetic fuels from hydrogen and direct captured air. So we synthesize some liquid fuels here, liquid hydrocarbons, net zero fuels from captured CO2 and renewable electrolysis, and then use some of that direct air capture to simply offset the continued use of fossil derived fuels. So in other words, the only substitute for end-use electrification is increasing electricity supplies overall. So there's no real way around this challenge of substantially expanding the share of carbon-free electricity in our overall energy mix. It's just a question of whether it's directly supplying end loads or acting as an intermediate fuel supplier, as it does to a greater degree in the E- case. So what that leaves us then for the electricity sector is twin challenges, each of which would be substantial on their own, and when combined, really drive home the scale of the overall challenge for the electricity sector. So what we need to do is simultaneously drive carbon emissions down to 0 by 2050, while simultaneously more than doubling electricity demand. In these scenarios, E+ and E-, we see total demand go up by approximately 150% by 2050, so more than double. And what you can see here is the current energy mix in 2020, the electricity supply mix in 2020 by fuel type, which is about 40% carbon-free already, including 20% from nuclear in the orange box and another 20% from the combination of hydro and blue and all other renewables, mostly wind and a little bit of solar in green. That leaves us with 60% of our current electricity from coal and natural gas, with natural gas being the larger share in red. And across all of our scenarios, by 2030, that coal share is entirely eliminated from electricity by 2030. And over time, we have to shrink and replace the share of electricity we get from natural gas as well. And what that means is the gap between this rising demand for electricity and the existing resources that we have here. And I do show the nuclear share declining. We assume half of the existing nuclear fleet can operate to 80 years, whereas the remainder retires for either economic or safety reasons. The gap between these demand bars and the existing capacity we have gives us our increased demand for new carbon-free electricity each year throughout the next several decades. So if we put those two lines into perspective, first we can see superimposed total 2020 zero carbon generation. So this is that 40% of our electricity supply we get from wind, solar, hydro, nuclear, biomass, et cetera. And what this shows is that sometime between 2027 and 2028, so within the next decade, we have to double all electricity that we get today from zero carbon sources. Then sometime between 2038 and 2040, we have to provide enough new carbon-free electricity to double all current US electricity generation. In other words, we have to basically rebuild the entirety of our energy supply over the next 20 years, which it took us 160 years or so to build our current electricity system. And then depending on the pace of electrification, we basically have to do that all again within the next decade. So we have to build a dramatic amount of new carbon-free electricity to replace our current energy system. And if we think about that in terms of average annual addition rates, and we normalize the capacity by capacity factor to an average gigawatt of output, we can think of an average gigawatt as the output of a large 1,100 megawatt nuclear power plant on average with, say, a 90% capacity factor. So a single AP1000 nuclear reactor, for example, provides an average gigawatt over the course of a year. Or alternatively, an average gigawatt is enough to supply about 850,000 US households. So a substantial size city's worth of residential electricity demand for an entire year. The average rate of additions that we see across these scenarios then in those terms is on the order of 35 to 37 average gigawatts per year, or the equivalent of bringing on 35 to 37 new nuclear power plants every year between now and 2050. And if we compare that to how fast we've been going recently, you can see these bars down below. The red is the green color here is the average annual growth in non-hydro renewables, so mostly wind and solar, between 2010 and 2018. And this is the second bar is the peak single year of additions, which was 2016. So you can see we basically brought on board the average of 3.5 average gigawatts of wind and solar over the last decade, and a maximum of only 5.3 average gigawatts. So, a seventh of what we need to achieve in order to be on track. So we need to be dramatically accelerating the growth of low carbon sources. If we look a little bit further back into our history from 1981 to 1990, we rescale for the size of the population to compare between different times with differing amounts of resources available. The US brought on nuclear capacity at a sustained average rate of 7.4 average gigawatts per year over the decade from 1981 to 1990. So even that growth rate is still a fraction of the rate that we need to achieve to be on track for these kinds of deep decarbonization goals. If we look a little bit further afield to other countries, Germany, on a per capita basis, has grown at about double the rate that we have, their 900 renewables. So if we scale them per capita to, again, account for the differing sizes of our countries, Germany grew at an average rate about 6 average gigawatts of renewables between 2009 and 2018. And sorry, the label got cut off, but it's about 12 average gigawatts in a single year in 2017. The largest annual sustained addition rate in the United States was for natural gas capacity in the 2000s, when we restructured electricity markets and unleashed a large amount of investment in combined cycle and combustion turbine capacity. That was on the order of 23 average gigawatts of sustained capacity per year for a decade, which is starting to get us closer to the rate that we're talking about in this study. And then finally, the fastest sustained annual rates on a per capita basis, at least, of new zero carbon generation were achieved by France and Sweden in the 1970s and 80s in their nuclear build out rates, which are at least on par in terms of the order of magnitude with the kinds of capacity additions we're talking about in our net zero scenarios. So these are really clean energy growth rates that are without precedent, and to be achieved will require substantial policy commitment, clear and sustained public support for the scale of infrastructure deployment we need and the impacts on our landscapes that will occur, and proactive investment decisions by the business community supported by the previous two conditions. Without those three, solid policy environment, broad social license and sustained support from the public, and proactive public investment private sector investment on the timescales we need, I think it's unlikely that we're going to see the growth rates that we're talking about. And that's why we hope the study will put the scale of effort into stark relief and clear focus so that we can have a serious conversation about the kinds of policy measures and commitments that are needed to redirect investment at the pace that we're talking about. We have the capital, the financial, human, and physical capital, the endowments, natural endowments of resources in this country to do this kind of investment. The total cost of these scenarios, I didn't include this graphic, in terms of the percentage of energy expenditures that we spend on energy as a percentage of GDP, is in line with what we've been spending historically. So this doesn't require us to dramatically sacrifice on the economic front, but it does require us to reorganize and focus our investments in ways that lead to sustained growth and investment in these resources over time. So let's look at the individual components then. As you can see, renewables played a key role in this. They're going to take center stage across all of the scenarios, and that's driven largely by the good news in recent years, which is that wind, solar, and battery costs have fallen dramatically over the last several decades, or last decade itself. When we've basically seen a 90% reduction in the cost of solar and lithium-ion battery packs over the last 10 years, and a 70% reduction in the cost of wind. And we expect those cost reductions to continue to some degree over the next couple decades. As such, wind and solar become dominant in all of our scenarios. We have our E+ and E- scenarios here, where you can see wind and solar provide on the order of 70 to 80% of total electricity generation by 2050, up from only about 10% today. We also ran, because of the important role of renewables here, we ran two other scenarios, a growth limited case, RE-, where we limited the growth of wind and solar to their historic maximum peak addition rate per year. And then an RE+ case where we tried to go 100% renewables, displacing all fossil fuel use and nuclear by 2050 throughout the economy. And you can see that even in the constrained growth rate case, renewables are still about 45% of our energy use by 2050. And of course, in the 100% renewables case, the growth is just staggering. The pace of new additions that we're talking about now in total gigawatt terms has to steadily ramp up. For comparison, before COVID-19 disrupted the economy, the EIA was projecting that this would be a record year for US wind and solar additions on the order of 35 gigawatts of combined additions. And you can see that these are the 5-year sustained average rates that we need in each of the 5-year increments between now and 2050. And so that pace that we were expecting in 2020 is on par with what we need in the first 5 years of expansion. But beyond that, we need to be rapidly growing the overall share addition rates for wind and solar, so that by 2030 at the latest, the average annual additions of wind and solar in the United States are on par with the single national maximum year of expansion globally, which was China's expansion of wind and solar, actually in 2 different years. If we combine PV from 2017, which is 54 gigawatts of expansion, and 30 gigawatts of wind in 2015. That's the kind of pace that we need to be at by the 2030s. Even though wind and solar play a central role, we don't see the 100% renewables case being the most cost effective. And even in the 100% RE case, we actually see a not 100% wind and solar in the outcome. So this is that case here. In fact, across all scenarios, we see roughly the same amount of firm generating capacity as we do in today's power system, which is about 1,000 gigawatts of firm generating capacity. So the combined cycle combustion turbine plants, CCGTs with carbon capture, biomass and nuclear, et cetera, that play this role of firm resources is really on par. It's 600 to 1,100 gigawatts of firm capacity needed by 2050 across the range of scenarios. And in the cases that are 100% renewables, and in many of these others, we rely a lot on gas plants, combustion turbines and combined cycle gas plants that switch over time to run on high hydrogen blends, so that they run on hydrogen and methane, where in these scenarios, the remaining methane is offset by negative emissions. And in the RE plus case, the methane comes from methanation of hydrogen and carbon dioxide from carbon neutral sources. And these are expensive fuels, but gas plants are very techno-economically suited to run alongside wind and solar because they have low fixed cost and high fuel costs. And so the high relative fuel costs of the remaining hythane blends or hydrogen methane blends is relatively inconsequential in the total system costs. And they make for a good pair to wind and solar, which are all energy value with no fuel cost, but very little capacity value. I think since I'm short on time, I'm going to skip this next section, which starts to walk through why we need to have both wind and solar resources. Maybe we can come back to this in questions if we have time. But the upshot is that wind and solar play different roles in the energy system than firm generation sources like coal and gas do in our system today, and zero carbon firm generation sources need to in the future. And so while wind and solar and batteries are going to be star players, just like it's difficult to win a game of basketball with only point guards on the court, we need to round out the rest of the overall low carbon energy team to complement wind, solar, and batteries in their starring roles with other resources to complete the overall team, with each type of resource playing their right role on the court. So in my other research, I've published on the differing roles of firm low carbon resources and of differing, electricity resources in a decarbonized electricity system. And we recommend a taxonomy with 3 different categories of resources. The first being fuel-saving variable renewable resources, which is where wind and solar play their key role in the system. We call them fuel savers because when they're available, they have no fuel cost and they back off and avoid the fuel and variable costs associated with other resources that do consume fuel, like biomass or zero carbon gas sources or gas with CCS. And yet at high penetration levels, they deliver very little capacity value because at the times we need firm capacity are exactly the times when the wind and solar output is low for a prolonged period of time. So their primary value is as fuel savers, either by displacing fuel consumption in the power sector or through the use of flexible end-use loads like electric boiler, dual fuel boilers, or electrolysis, displacing fuels in other sectors where the hydrogen or boilers can displace liquid or gaseous fuels in other end-use activities. The second category we call fast burst resources or balancing resources, and this is where short duration demand response or price responsive curtailment of loads, flexible rescheduling of short-term demands, and battery storage play their role. These resources are all very flexible and provide a lot of ramping and capacity value, but can only be sustained for short periods of time, either because they're energy constrained like batteries, or because the cost of sustaining their demand curtailment over long periods gets very high. And that makes them good for filling in on the hourly or intraday timescale for the variability of wind and solar on those timescales, but not for fulfilling it over sustained periods of time to manage prolonged or seasonal declines in wind and solar availability. What that leaves then is the final category of firm low carbon resources, where we define firm resources as technologies that are not energy constrained and not weather dependent, and therefore can supply energy for any period of time for as long as needed by the system operator in any season of the year. And this includes technologies like geothermal and biomass or renewable derived gases, so renewable firm low carbon resources, as well as nuclear and gas or coal with CCS, which are non-renewable zero carbon sources. Large reservoir hydro systems and very low cost, long duration storage might be able to play this role as well, so we put them on the edge. But large hydro systems like they have in Quebec or Sweden or Norway are kind of limited in their generalized utility in other regions. And firm storage technologies that are low enough cost to meet this role remain far off from current commercial activities. So in the near term, wind, solar, and batteries, and a continued transition from coal to natural gas in regions that have not completed that transition can drive emissions reductions at the pace that we need to be on track to net zero by 2050. But fully decarbonizing our electricity system requires one or more clean firm or firm zero carbon substitutes for natural gas and the retiring nuclear capacity that will go offline between now and 2050. We explored the role of firm low carbon resources in great detail in this Joule paper that was published in 2018 and can be found at this bit.ly link here, where we ran a wide range of scenarios and a detailed capacity expansion planning model that included detailed operating constraints, including unit commitment decisions and ramping constraints. We ran several different technology cost combinations with high, medium, and low costs for wind, solar, and batteries, for nuclear and natural gas as CCS, and for the availability and cost of biomass and biogas fuels or zero carbon fuels. What we found across all cases, when we compared those that included firm low carbon resources in the portfolio versus those that only had wind, solar, batteries, and demand flexibility, or in other words, the current technologies that are contributing the most to our low carbon portfolio, we found that when we tightened the CO2 emissions limits, which is shown on the x-axis here, we're at about 500 grams per kilowatt hour today in our current system. So this is about a 70, 80, 90, and then 99 and up % reduction in emissions shown here. That between now and an 80% reduction in emissions, the costs across the range of technology scenarios, which are the different colors here, are not all that different if we have firm low carbon resources or if we don't. And that's because we can continue to rely on natural gas plants with relatively low carbon intensity to play the firm low carbon role that we need in the system at those levels of emissions. As we transition though to zero carbon goals or deep decarbonization goals, the role of natural gas plants without carbon capture and storage or without switching over to zero carbon fuel blends is substantially constrained. And there, the cost of continuing to displace natural gas with a combination of fuel saving renewables and fast burst batteries starts to stretch these technologies out of the role that they should be playing, the starring role on the team, and into other roles that they're not well suited. So that we need an increasingly large amount of wind, solar, and battery capacity to displace each marginal unit of natural gas. Because basically we need the wind and solar output in precisely the times when wind and solar availability is the lowest during sustained periods of low wind and solar output. And so we either need to dramatically overbuild wind and solar to eke out a little bit of production when capacity factors are low, or we need to store a huge amount of that energy from high productivity periods in batteries and transition that energy to times when it's needed, both of which are not what wind and solar are well suited to do. In contrast, when we have firm low carbon resources available, the cost of decarbonization across any particular technology scenario that we chose falls significantly by 10 to 65% across the range of cases. In addition, as you can see, even though any individual technology case falls, it actually is cheaper in some cases in our most conservative case, for example, in the northern system that we ran, of the two systems, we ran a southern case as well, that even the most conservative case, which is today's cost, so no future technological improvement, is actually cheaper at zero emissions than the most optimistic low-cost wind, solar, and battery scenario that we ran at zero emissions. So you can also see that in addition to reducing the cost of any given technology outcome, the cost sensitivity to uncertainty in future technological change is also dramatically reduced when we have more firm low carbon resources available. So in this case, when we don't have them available, the system costs are substantially dependent on how cheap wind, solar, and batteries become. Whereas in the more diverse cases with a complete team of options, including firm low carbon generation options, the total variance in energy costs is substantially reduced. It's still significant, and improved technological change is important to reaching the lowest cost outcomes, in which the total cost of decarbonization is only modestly above today's energy costs. But the total sensitivity is dramatically constrained, which leads me to conclude in our paper and elsewhere that having a complete set of firm low carbon generation options to complement wind, solar, and batteries is a lower cost and lower risk strategy to ensure we can reach zero carbon emissions at a reasonable cost. Finally, and I'll just close here because this is where much of the net zero emission study, a Net Zero America study is focused, and where our continued work on downscaling the modeling results is focused, is that none of these strategies will work unless we can secure social license or broad public buy-in for the scale and type of infrastructure that has to be deployed to transition to a net zero emissions energy system. These social license challenges are unavoidable, whether you prefer wind and solar or nuclear or carbon capture, whatever favorite technology you might want. We rely on all of these technologies to varying degrees in the lowest cost scenario, and all of them face certain challenges around securing social license. So in the net zero scenarios for the overall economy, we rely heavily on biomass, for example, using at least 700 million dry tons per year of biomass feedstocks, which is fed into hundreds of different new bioconversion facilities to produce hydrogen, pyrolysis to liquid fuels, and for power plants with CCS. At the same time, to free up a lot of land without making greater stress on our agricultural lands, in all of our scenarios, we assume we can transition the 20% or so of our prime corn production lands that are now dedicated to ethanol to other higher yield bioenergy crops like miscanthus and switchgrass. A transition that makes a lot of economic sense, but requires a wholesale transition in the activities of farmers and farm communities across a large portion of the country. For wind and solar, we have to be able to site tens to hundreds of gigawatts of new wind and solar annually and sustain that for decades, as I showed you in earlier slides. This has a substantial overall land impact, while the total direct impact of the land taken out of production by, say, wind turbine pads, et cetera, is much smaller. The impact is quite pervasive in terms of the visible impact of wind in particular across the landscape. And we need somewhere on the order of 2 to 4 times New Jersey's land area to site wind and solar nationally across these scenarios. And we need to dramatically expand interstate transmission capacity to tap into these resources by at least twofold. On the other hand, it's not like carbon capture and storage or nuclear power are particularly easy to site either without social license. Most of our scenarios don't rely a lot on nuclear unless we use more optimistic cost assumptions for future nuclear costs than we did in our base case assumptions. But in the cases where wind and solar are constrained, like our RE minus case, nuclear picks up a lot of the slack. And in that case, we have to site several hundred new reactors, or 250 gigawatts of new reactors, which means either on the order of 250 gigawatt scale reactors or several thousand small modular reactors by 2050. And there's no way we'll be able to do that unless we can achieve a national consensus on spent fuel storage solutions for both the existing fleet and any new nuclear plants that be built. And finally, carbon capture, use, and sequestration plays a critical role in a lot of our scenarios. In our main case, our E+ case, we mapped out the pipeline network that would be needed to capture CO2 from all of the various point sources and bring them either to saline basins for injection or to facilities that would use the captured carbon for fuels production. And that means about 17,000 kilometers of interstate CO2 pipelines for a trunk network and 45,000 smaller diameter spur lines that would connect up point sources to that trunk network. And in the by 2050, we're sequestering on the order of about 1 to 1.7 billion metric tons of CO2 annually, up from just on the order of a few tens of millions of metric tons today. So all of these require substantial scale-ups in infrastructure, substantial scale-up in technologies and industries that are immature today, and substantial deployments of human and physical capital across the United States. And none of that is going to occur without broad social license and policy buy-in. And so the remainder of our report, which we're working on finalizing now, is really focused on downscaling and looking at a fine granular geospatial scale at the kinds of deployment of infrastructure we need across the country to try to start a national conversation about the kind of transition that we have to undertake if we take the climate challenge seriously, and the kinds of roles that various industries and populations and communities across the country have to play in that transition. So I'll stop there. Stay tuned for more from Princeton Net Zero Study this summer and fall. And happy to take questions with whatever time is remaining. I know I've filibustered most of it, but I'm happy to stick around a little bit longer if you have time to chat for a few minutes. Thank you.
Thank you, Jesse. Thank you so much. I would clap, but it's going to be only me this time.
Yeah.
So if you have a question, we have several ways on how we can proceed with the audience. So either you are welcome to type your questions in the chat or raise your hand. And when I see that you raise your hand, I will unmute you. And okay, we have one unmute. It's going to be Robert. So I'm going to allow Robert to talk. Go ahead.
Hello, can you hear me?
Yes.
Okay, perfect. Thank you very much for that great talk. Very insightful. I have a small question concerning CCS and nuclear. If we look at decarbonization roadmaps and studies from the basically last 10, 15 years, nuclear and especially CCS has been one of the main hopes to deal with decarbonization for exactly the reasons you mentioned, but then we observe huge practical issues in reality, especially for CCS. There are a lot of demonstrating projects that are not continued anymore, or which costs were a lot higher than expected. And also for nuclear, actually, since the 80s, so the time range you showed for Sweden, for example, we saw an increase in costs per unit and per reactor in nuclear. Yeah. So I guess my question would be, how do you evaluate this trend? Do you think there will be a change, or what should be done to overcome this trend that we actually have been observing from a practical point of view?
Great question. Yeah, and that's it's one of the key uncertainties, and it's not. One of the things we sort of point out is it's not an exogenous, factor, right? We have a lot of choices to make about how we want to shape the course of those technologies. The reason that wind and solar and batteries have gotten so much cheaper over the last decade is because of sustained and proactive public policy support across a variety of jurisdictions, including the United States and Germany and Spain and China and elsewhere. And so, with 20 years, and particularly even the last 10 years of public policy support, we've managed to help support investment for the private sector, incremental innovation and improvements in those technologies and their scale up and maturation of the supply chains in ways that have dramatically reduced the costs. Nuclear and CCS are not exactly the same type of technology. They're not small, modular, manufacturable components. And so we shouldn't expect exactly the same kind of technological progression. But we should expect that public policy support and proactive support for these technologies on a similar scale can improve the technologies and at least give the private sector a chance to do so. And I think what we're seeing is actually, I would classify the CCS story a bit more optimistically than you did, although I think I agree that the nuclear story has been pretty pessimistic, at least in the Western countries recently. There are dozens of CCS demonstration projects actually that are at the 1 million metric ton capture scale that have been built over the last 6 years or so. And all of, basically in every end use case that we could want. So we have them for steam methane reforming facilities that produce hydrogen from natural gas. We have them for ethanol facilities. We have them in power plants. We have them in sour gas cleaning facilities, sort of a whole bunch of different applications across sectors. And we've seen the costs fall pretty significantly for those as well. So for example, the costs of post-combustion carbon capture with amine scrubbers has fallen by about 60% over the course of the first 3 or 4 demonstration projects. Okay. So I think, and then just recently, the United States enacted for the first time a substantial deployment policy incentive, the 45Q tax credit for carbon capture, storage, or use, which is worth $35 per ton for capture and use, and $50 per ton for sequestration. That was passed last year, about over 18 months ago, I guess. And the Treasury just finally released the guidance on how to actually claim that credit. And so there are a bunch of projects that are likely to move forward, spurred on by that tax credit over the next 7 years. And that's, I think, where we're going to see that, and other policy supports, where we're going to see whether this technology can can actually contribute at the scale that we want. For new nuclear, we need a whole new generation of nuclear plants that are constructed in a very different way, at least in the West. And in the gigawatt scale, huge civil construction engineering projects that we've seen have really not gone well in Western countries. And that's not just unique to nuclear. We're not great at building giant bridges or stadiums or all kinds of other complex engineering projects. But in countries that are like the Middle East, regions that are like the Middle East and China and South Korea, they have been building nuclear plants at a much more affordable cost and much more on time and on budget. And so I think in other countries, nuclear will play a bigger role in the near term. But I think we're going to need to have smaller modular reactors, or at least very different approaches to construction that can overcome those challenges for nuclear to play a big role.
Okay, thank you very much.
Thank you, Jesse.
Yeah, great question.
The next question is from Matthias Berger. Matthias, go ahead.
Hello, can you hear me?
Yep.
Okay, great. Thank you for this very interesting talk. I've got a couple of questions, but I guess I'm just going to ask a few of them right now. Maybe would it be possible to follow up offline afterwards as well?
Yeah,
possibly.
Sure.
Okay, cool.
Yep. This is my contact info if anyone wants to reach out after.
Okay, wonderful. So what I was going to ask is mostly about the carbon accounting which is being made. So I assume there's a carbon budget which is imposed.
Yeah.
Is it imposed on the full trajectory that's being optimized, or is it
That's right. We assumed a straight line reduction to negative 170 million metric tons by 2050.
Okay. And so
we didn't optimize the shape of the trajectory itself, which could be a whole other exercise. Yeah.
Okay. So I guess you assume specific emissions for a bunch of technologies, right?
Yeah.
And for RES, do you take LCA values into account, or do you assume no specific emissions from RES whatsoever?
So we don't directly assume. It's not the upstream materials uses are not endogenous, but we do maintain the current scale of all industrial activities. And count the emissions from cement and steel and everything else, and do decarbonize all of those. So if there is an increase in total steel production or cement use or whatever in order to decarbonize, then we would not be accounting for that. But if the total amount of steel and cement, et cetera, is on the same order of magnitude, then we have accounted for decarbonizing those sectors.
Okay, and so in the US right now, are most materials sourced locally, or within the United States, or does a lot of that stuff come from outside?
Yeah, so we depends on the products. We assumed no increase in imports in materials to try to prevent any increased offshoring and contributing. But whatever current levels of imports are not on the US accounting books for the purposes of this study.
Okay. One last quick question, and it's regarding the role of direct air capture and maybe zero net emissions gases. I guess you went over that quite fast, but I was wondering whether you could expand on that a little bit and maybe very briefly state in which scenarios they play a role.
Yep. Yeah. So we assume
the scale of the facilities which would be needed for that purpose as well.
So we assumed a fairly high cost for for direct air capture in this case of about $660 per ton captured, which is fair on the fairly higher end of things. The more very optimistic cases are more we'll get to eventually to about $100 per ton or 150. And so we use it at that high level, and at that level, except for in cases where we need to, except for in the cases where we're constrained in the degree of end-use electrification, and we need a lot of additional offsetting of fossil fuel use or production of synthetic fuels from carbon neutral sources, we don't have a whole lot of direct air capture in our model results. So it basically acts as kind of a safety valve in cases where we find it more difficult than otherwise would be to decarbonize some of the last liquid fuel carriers, jet fuel and diesel being the two main ones that drive the challenge. And so if we have enough biomass and use electrification to reduce those to the levels in the main cases, we don't need any direct air capture. But we do get a lot of negative emissions from biomass with CCS. So not for power generation, but largely for synthetic fuels production and hydrogen production from gasification, where we use biomass, gasify it into hydrogen, and capture and sequester the CO2 which then can offset some continued use of fossil fuel use in other sectors.
Okay, and what's the cost of sequestration that you assume in there?
I don't have it in the slide. We have a whole range of supply curves that we built up depending on the region and the type, and it goes up as we use more. It's between, like, for the very first share, which is EOR, it's like -$10, you get paid for it, but that's very small. And then it goes up to like $70 per ton captured, I think, at the high end of our supply curve. Okay. And we cap that out at just under 2 gigatons per year at the high end of that supply curve. And actually, most of the cases get priced out, so they don't use the full supply curve. The high end of the curve is too expensive, and it doesn't want to use the rest of it.
Okay, thanks.
Yeah, but there'll be more on all that and details in the report, but we took a good amount of time with it.
I think the next question is going to be related to what you were just talking about, related to H2. Miguel, are you ready?
Yes. Hi, this is Miguel Mastino from Chemical Engineering. Thanks a lot for the presentation. Very interesting. And yes, as Yuri said, my question is related to the role of clean fuels in all of these different scenarios, and specifically the role of hydrogen,
yep.
And perhaps even.
Oh, you're on mute again. Lost you for a second. Miguel, you're on. There you go.
All right. I think I'm unmuted now again.
Yeah, now you're good.
So yeah, the question that I had was mainly about the role of hydrogen in this whole picture. Under the current technological state of the art, producing hydrogen via electrolysis is significantly more expensive than doing so from natural gas. And that had been preventing the implementation of large-scale electrolysis projects.
Yep.
And when you look at CO2 electrolysis, then the picture is even more grim. So I wonder if you have some thoughts about what will need to happen for these clean fuel technologies to actually be implementable and play a significant role on this picture, in particular with respect to their possibility to compete with fossil fuels.
Great question. Yeah, so we do actually still see some hydrogen so hydrogen comes from 3 sources in our results, not just from renewable electrolysis, although that is a big chunk of it by 2050. In the nearer term, it mostly comes from autothermal reforming of natural gas with CCS. And so that is the most cost-effective current near-term technology to produce hydrogen, so-called blue hydrogen from natural gas with CCS. And then what ramps up in the 2030s and 2040s is a lot of both biogasification to produce hydrogen with carbon capture, and renewable electrolysis to make use of increasingly low-cost wind, solar, and electrolysis equipment. So if we spend the next decade improving the cost of electrolysis and continuing to deploy wind and solar and driving their cost curves down, and we continue to improve biomass gasification and carbon capture technologies, then we'll have a full suite of different ways to produce hydrogen at relatively low cost from a variety of fuels. And then hydrogen ends up playing a pretty substantial role, both as an end-use fuel, blended with methane in pipelines, blended at a higher share in power and combustion turbines, along with the hythane blend from the pipeline. And then also used in the electric hydrogen, dual fuel boiler setup. Used in some directly in some end use activities like steel production. So we assume all iron reduction in steel production is direct reduction with hydrogen by 2050. So that's another big use. And then it also is a feedstock, intermediate feedstock for some of the synthetic fuels produced by Fischer-Tropsch and methanation. So, it's a big piece of the puzzle, and we're not ready to do it at scale today with anything really other than natural gas with CCS, which itself the CCS part is still relatively costly. So it's a major priority for the next decade to focus on improving all 3 of those routes.
Thank you.
Thank you, Jesse. Jip, you're next.
Hi, thank you so much for your great talk. My question is related to the decarbonization of the electric power sector. And I'm wondering, in your simulation, what kinds of policy measures are you assuming to be implemented to achieve such emission goals?
Yeah.
And then this question is also related to the fact that in the United States, in the one wholesale electricity market, there can be multiple different states having different policies implemented in different time scales, right? So I'm wondering whether you have considered the interactions among the states or the advantages or disadvantages of such states.
So those are great questions. They're questions that we explicitly are ignoring in this study. We are trying not to provide any kind of policy recommendation or analysis here. Our goal is to provide an engineering blueprint for what has to get built if you want to do this, and the kinds of costs that that would be entailed in the sort of landscape and infrastructure deployment across the country. So we were explicitly at the beginning of the study decided not to try to model the impact of policy and just to look at the straight line emissions goal and the lowest cost way to achieve that. That, of course, then provides a blueprint for what we need to build, but not how are we going to go about building it. So it is not a plan. It is not a recipe. You know, it is a blueprint, the schematic for what we might want to build. And the goal is to then seed conversation about the kinds of policy measures that need to happen and ground those conversations in a detailed understanding of the engineering and infrastructural challenges. So all great questions, not ones we address explicitly in the study. I have lots of other thoughts personally, but probably not the best to get into right now. And I do have to jump off and maybe after the next question.
Yeah, we just have one last question, which is audio, and the rest are text. I can forward it to you and we can take it offline. Francisco, you're on.
All right. Hello, I also like your presentation very much. Thank you so much.
Thank you.
I have a question regarding sequestration. CO2 sequestration looks to me like storing nuclear waste. Both of those things we are just, if we implement them now, we're just delaying the problem for future generations. So, but those seem to be very important factors in achieving this goal. But aren't we putting the future of people in a different kind of danger, moving from having CO2 in the air to having CO2 in the land and the nuclear waste somewhere stored in the nuclear plants?
So I'll give you my view on both those challenges. Yes, there is some degree of long-term risk associated with both, but first of all, it is a wholly different type of risk than unchecked global climate change. So let's be clear about the scale and magnitude of the threats that we're talking about. And you know, in any society, we have to mitigate and minimize risk, but we never eliminate them. So you're right, there's a trade-off here. I think the trade-offs are pretty overwhelmingly on the side of stopping climate change first and then mitigating those other challenges second, but that isn't to say that those should be ignored. I don't think that CO2 sequestration is anything like nuclear waste. They're differing on both their magnitude and their intensity. So nuclear waste is incredibly compact. There's only about 50,000 tons of high-level nuclear waste from the entire history of US nuclear power production, which has provided a fifth of our electricity for the last several decades. 50,000 tons is not a lot. You could stack it in dry cask storage containers, which are perfectly safe to stand next to, for in three football fields worth of space, so 3 soccer pitches. So it's really very little high-level waste, and the reason we've not had a solution to it is not a technical one, it is a political one about where we want to put it. Other countries have done a much better job of managing that political question through consent-based siting processes, and Finland has actually sited and has begun construction and will soon open a long-term geologic repository for spent nuclear fuel. So I think this is very much a solvable challenge and one that is wholly different from the complexities and scale and impact of climate change. But of course, it certainly needs to be solved if we're going to have nuclear play a larger role in our future. CO2 sequestration is a very different challenge in the sense that it's a lot larger. We're talking about billions of tons per year sequestered, as opposed to, you know, a few thousand tons in very concentrated form. On the other hand, the risk is incredibly different, right? You know, if released, high-level nuclear waste is one of the most toxic, you know, deadly substances available, right? It's a very concentrated risk. Whereas CO2, if it leaks, is going to leak slowly. It's going to leak into the atmosphere, and it's going to contribute marginally to whatever degree of climate change already occurs. So it's a very different risk, and I don't think it's at all comparable in terms of its risk to human health as nuclear waste. And I think we have a strong reason to believe that we can store and sequester gaseous substances underground for millennia, because that's exactly what natural gas and oil are, right? They're sequestered hydrocarbons in geologic areas. And so if we continue to demonstrate and monitor the efficacy of CO2 sequestration in various geologies, which we've been doing steadily for the last 15 years or so, I think we can be confident in the types of geologies that can store CO2 emissions for millennia versus those that are too risky to store in. And the confidence levels are very high amongst those who study this for their primary field of research, which is not mine. So I'm just immediately summarizing what I know from those who study this as a living. The question is not about whether we can store it safely, but whether we can find good places where we can keep up the level of injectivity at the scale that we need. So they're more worried about sort of running out of pore space and injectivity than whether or not the CO2 will stay down there.
All right. Thank you.
Thank you for this answers and for the presentation, Jesse. It was a fantastic experience. Unfortunately, again, we cannot clap you at this moment.
It's okay.
But hopefully,
yeah, you can. You're unlimited. Thank you.
But hopefully, there'll be a chance to have you over here in person sometime later.
Yep. Would love to spend some time with you all. All right. Be safe and be well. And thank you so much for inviting me.
Thank you. Goodbye.